Hello, Trick Class. We're going to look at the alterations of the sine and cosine graph and also why it's happening based on the definition of sine and cosine that we saw in the unit circle. Let me move my head out of here. So what we got in this grid, this is what you guys saw, but you didn't have the sine and cosine over here. You just saw what was happening here and you wanted to describe what you're seeing, but I also wanted to add in here what it's doing to the graph of sine and cosine. So first of all, we've got t equals 0. That is our angle. So as I rotate around, you can see the angle is growing, and you can see the purple that we see there. That's the angle. It also shows up over here as how far we rotate it. So again, the angle of rotation in the circle is are the x points on the graphs of sine and cosine. And you can see the orange here. That's the x coordinate of this point. I've gone to the right from the origin, the orange amount, and I've gone up the red amount. The orange is what we're plotting here. It's kind of being rotated and plotted vertically as the output when the input is this angle. And then the red, that's the sine. It goes up and down just like it does on the picture. But anyway, as we rotate around, you can see the x is now negatives on the other side. So now we're dropping down below the x-axis. Y is still above, so we're still above on this part. And then as we keep rotating around, you can see now we dip below. Y is now negative, so we're down below. X is still negative, so we're down below. So the x's and the y's are what sine and cosine represent, the values in the unit circle. Now, when we have a sinusoid are alterations of sine and cosine waves. And that's what we're seeing here, right? All the different ways that we can alter them. We can multiply the angle by a number, add or subtract to the angle. We can multiply the output of sine and cosine by a number, and then we can add or subtract to that. So when we do all that, we get these alterations of the sine wave, and they're all based on what it does to the graph in the unit circle. So the first thing I want to ask you guys to do was look at A. What happens when I alter A? So I'm going to go down here and I'm going to turn on the altered circle and turn off the original. And what you're going to see here is when I make A bigger, there is the original unit circle, and then here is the altered A circle. And you can see what that does with the graphs over there. It stretches them, makes their amplitude bigger. Well, the reason is because the radius is now bigger. A is the number that's in front of cosine and sine. And the first question to ask you was about solving that cosine equals x over r and sine equals y over r for x and y, and you got a cosine or r cosine and r sine. Well, a is in the position of r, so a is directly giving us the new radius. It's stretching out the radius. The radius was 1 and now the radius is 2. It's whatever this number is. That's stretching up. This is what we call the amplitude. The amplitude is now the maximum minimum values from that stretching out of the radius, making the radius bigger. All right, and as we go around, the same thing happens as it happened before. This red is our x, the green is our y. So there's the little red piece that's coming off of the original circle, and the y, that's the y coordinate, that's the sine function. That's the sine of this altered A times the sine. So as we go around, we get the same thing that we saw before. We're just stretching it out to a radius of 2 rather than a radius of 1, which makes the amplitude bigger. All right, notice the zeros of the sine and cosine function. There's the 0 of the cosine function. It's the same if A was 1 or A was 2. That will always maintain if all we change is A, are the place where the zeros take place of the sine and cosine. All right, let me move A back down. All right, the next thing I asked you guys to look at was B. Now, before I look at the graph of B, I'm going to zoom in on the circle. We could tell when we altered A, we could easily tell in the unit circle what's going to happen. We're making the radius bigger. But now when I alter B, it doesn't look like anything is happening on the unit circle. So as B changes, it doesn't appear that anything is changing with our point on the unit circle. But you can definitely see the effects on the graphs of sine and cosine. Watch what happens when I alter B on these graphs. When I make B bigger, we can see this squeezing in towards the y-axis that takes place. And now when I make B smaller than 1, we can see it's stretching out. Think it was like a slinky or a spring. It's being pulled in, it's being pulled out based on that value of B. So I'm going to pull it up to 2, And you'll see why you don't see it on the unit circle. It's because it has to do with the speed that we move through the unit circle. When I play t this time, you'll see that let me put the original circle on there as well. Our original circle goes through there at the green dot is the original circle for the values of t, for the values of the angle. And you can see the purple dot, that's our altered, it's going through there much faster. So the value of b is kind of like the speed that we're rotating through the circle. And we are, because right now we've got b as 2, we're going double the speed that we're going through on the original circle. So if I slow this down, you can see that that purple dot slows down and the orange dot is catching up with it. When it's 1, they're going the exact same speed. And then if I go below 1, you can see now the purple dot is moving slower than the green dot. And so again, b is just affecting what we call the period, how long it takes us to get through one revolution around in the unit circle. And then when we look at it as a sine wave, it's how long does it take us to go through in a complete wave. So like for cosine, it would be from peak to valley back to peak. All right, that's happening in pi radians now. For sine, it's midline, peak, valley, back to midline. All right, so that is one period of sine, one period of cosine. So we're going through them much quicker when b is bigger than 1. We're going through them slower when b is less than 1. All right, I've got b reset back to 1, a set back to 1. C is something we call a phase shift. If you look at all these others, I have numbers, integers or fractions on the endpoints, but specifically for C, I have common radian measures as the bounds, because C is I like to think of it, let me make t go back to 0. I like to think of it like somebody with a bow and arrow and they're pulling back on the string before they let go. So this is kind of where we're going to start from. So we typically think of our starting position, standard position, as the positive x-axis, and we rotate up from the positive x-axis. But what C does is what we call a phase shift. It takes this starting position and it rotates it either back or forth by whatever angle measure we pick. So if I go up to pi over 2, notice we rotate all the way down to the negative y-axis, 90 degrees, pi over 2 radians. If I go up to negative pi over 4, that is going up 45 degrees into quadrant 1. And that's where we're starting from. So when t equals 0, I mean the beginning of the x-axis, our x-coordinate is already shrunk a little bit. It's typically up here, we're already down to here because we're shifting our starting location. All right, same thing with y. Typically y is 0, but because we have rotated, we've got a phase shift, we actually are starting up a little bit. And so then we start from that position. That's the initial position that we start from, and we'll return back to that position. All right, and then finally D1 and D2, there's two different ones. There's one for the cosine and one for the sine, the way I've got it written. But you can see D1 is going to be a shift horizontal from the center of that circle. And D2, because it's attached to sine, remember sine's a y-coordinate, that's a vertical shift from that y-coordinate, right? But what I want you to see when I move these, and I have completely new starting position for x and y, and I won't make them both 1, let me just kind of mix them up so we can get some different perspective. Now when I start rotating from there, the x has already been stretched out a little bit further than 1. All right, so cosine, let me drag it down. Cosine's a little bit higher than 1. And the y coordinate is typically at 0. Sine is typically 0 here. Because I've shifted up, sine is starting from a higher position. So now when I rotate, the x and y coordinates are defined by a new circle. You know, the center of the circle, D1, D2, has changed. That's D1, D2 right there. It's changed, and that's causing new x's and y's that were not possible when the center was the origin to show up here. So moving the center of the circle around makes a different collection of points that we can get. But notice they're all just shifted up and down by the exact same amount when we start rotating around. So just so you can see it, just that tiny little red that we're seeing right there is that little piece of the cosine. It's relative to the origin. It's not relative to this center position where the center of our circle is. We're plotting the x coordinates, right, when we're doing these graphs. So we're seeing this tiny little blip right here. That's the tiny little piece where it's negative. And this part right here is the sine. All right, again, if I shift this over a little bit more, now it's never negative. The x coordinates are never negative, and so we don't see the cosine graph shift down below the x-axis. Right? The y coordinates still have a little bit of a negative place right here, so we see that tiny little negative blip. So anyway, that is shifting the center, d1, d2, where we're altering that. And that's why we're seeing what we see with alterations of sine and cosine. It is strictly still based on the definition of the circle, but those positions in the circle get altered, so it alters the graph of sine and cosine.